Hello Math 1093, this is Dr. P with Domain Issues. Actually, this is about a lot of issues, one of which is domain issues. Really, I wanted to take this opportunity to talk about the graphs of logarithmic functions and how they are similar to or related to the graphs of exponential functions. So I've actually given us this little chore to do here. We're going to find the domain and range of each of these two functions, this one and this one. And we're going to find the graph of each one. We're going to draw the graph of each one of these. Okay, so the first function I gave us to work with was f of x equals the base 3 logarithm of x. And to develop a graph of this, we're going to use one fact over and over and over, which is this fact. The function log base 3 of x is the inverse function of 3 to the x. Okay, so a logarithm or a logarithmic function is always the inverse of an exponential function of some stripe, and that's definitely the case here. Okay, so first let's just review what we know about the function 3 to the x. So I want to use different colors for these. So I'm going to make this one blue. I'm going to make this other one here. Let's pick a different color. Let's pick purple for this. Okay, so I've got the blue function and the purple function. Blue exponential, purple logarithmic. All right, so for the blue function, I'm going to come over here. Let's just assume that each tick mark in this graph represents one unit. So I'm not cluttering this up with a bunch of numbers on the axes, because I'm probably going to want that real estate. But I know if I draw a table of values or make a table of values for 3 to the x, then I know that 3 to the 0 is 1, 3 to the 1 is 3, 3 to the 2 is 9, and I might also just take note that 3 to the negative 1 is 1/3. And that gives me enough information to start graphing. So I have 0, 1, I have 1, 3, I have 2, 9, I think that's 9 there, and then after that the function increases very sharply and goes beyond my graphing window. I know that 3 to the negative 1 is 1/3, so I'm going to put a point at about 1/3 there, and after that the function heads towards y equals 0 pretty quickly. All right, so let's see if I can draw a convincing graph of this. Here we go. Whee! Okay, and we do know that this graph will never actually reach 0. There's no way for 3 to the x to ever be equal to 0, or be negative for that matter. It'll always be positive, but it is going to continue to decrease. It's just that decrease is barely visible over here because I'm so close to the to y equals 0 so quickly. All right, anyway, that's the function 3 to the x. So now, if I want to know what the graph of the logarithm looks like, well, I can use the fact that the logarithmic function is the inverse function of the exponential, so I can create a table of values for this as well. And I could think through, well, okay, what is log base 3 of this? What is log base 3 of that? But actually I'm going to do something a lot quicker here, which is I'm going to take these ordered pairs and switch them, because I know that an inverse function switches the roles of input and output. So I know that I'll have 1/3 comma negative 1, I will have 1 comma 0, I will have 3 comma 1, and I'll have 9 comma 2. And you can actually check that these things are valid. For example, you can check that the log base 3 of 9 actually is 2, because 2 is the exponent that corresponds to a power of 9. I'm just saying that I can do this a lot quicker by switching input-output pairs. Anyway, so graphing all those ordered pairs, I get one here, I get one here, I get one way out here somewhere. There we go. And I get one down here. And my function graph looks kind of like this. Let's see if I can get this fairly accurate here. Okay, and this will continue to increase just very slowly. And on this side, the function decreases and never quite reaches the vertical axis. All right, so I think we're ready to talk about domain and range. For the function 3 to the x, I know that the domain is the set of all real numbers, so the interval from negative infinity to infinity. And the range is, what is the range? The range is the set of numbers from 0 to infinity, not including 0. In other words, only the positive real numbers. So for this inverse function, I'm going to switch those. The domain is going to be the set of all positive real numbers, and the range is the set of all real numbers, which the range might be hard to figure out from the graph, because it sure looks like the graph it does go down to negative infinity. But as far as going up to infinity in the range, it sure looks like it's stalling out here. but it's actually not stalling out. And the way that we know that is if this had some upper limit, if there were some horizontal asymptote here, then there would have to be a vertical asymptote for this function, for the exponential function. And there isn't. The exponential function goes to the right forever. It's just it goes up way, way faster than it goes to the right. So this logarithmic function will go up as high as we want it to go. It's just we probably won't ever see it in any graphing window that we might set. Anyway, so that's the domain and range of that function. So now let's shift gears again and talk about this other function here. Let's see, what do I want here? I want green. A nice darkish shade of green will work. Okay, so this function right here, 2 times log base 3 of x plus 4. So the way we're going to figure this one out is by transforming the purple function, which again is this function right here. Okay, so there's a couple of things to know about transformations that will help here. One thing is, what does it do when we replace x with x plus 4? All right, we did a little bit of this with trig functions, but just as a reminder, replacing each instance of x with x plus 4, like the entire object x plus 4, moves the graph 4 units to the left. That's something that I hope that you learned in the previous course when you worked on graph transformations. So it moves the entire graph 4 units to the left. And then, what about this 2 here? So multiplying the entire function value by 2 stretches the graph vertically by a factor of 2. All right. So what we're going to do is we have a few points on the purple function, and we also have a vertical asymptote. So these make little nice little guide points or features to keep track of when we transform. Okay, so I want to highlight those points. You notice I'm sort of darkening them in the picture, and I'm going to perform these transformations on them. All right. Oh, and let's also mark that vertical asymptote that the logarithmic function has. The logarithmic function, log base 3 of x, has a vertical asymptote at x equals 0. And if it looks like I'm kind of missing the vertical axis, it's just so that you can see the asymptote more easily. Okay, so anyway, so what do we got here? So we're going to move this whole thing to the left, which means that my new function is going to have a vertical asymptote at -4. There we go. So it's going to sort of head down in this direction. I'm just drawing the first little chunk of it. And then what about these points? Well, each point is going to get moved to the left and then also stretched vertically by a factor of 2. I guess I should have stretched the asymptote vertically as well, but if you stretch a vertical line vertically, you get the same line. So what happens when I take this point, for example, the one at 1, 0, move it to the left, and then stretch it by a factor of 2? Well, it actually just moves to the left because stretching something that's on the horizontal axis just leaves it there. So I'm still going to have a point here, just 4 units to the left. Now, what about this one here? Okay, I'm going to move that 4 units to the left, which would put it here on this point. But then I need to stretch this out by a factor of 2 vertically. So I'm going to stretch it from y equals 1 to y equals 2. Okay, what about this one now? So that point is at, I think that's at 9, 2. So I'm going to move it to the left 4 units. So now it's at 5. And then stretch it out vertically by a factor of 2. So it goes from 5, 2 to 5, 4. And then finally, what about this point? This was, what is that? That's 1/3, -1. 1/3, -1. Moving that 4 units to the left is going to put it around here, and then stretching it vertically takes it from -1 to y equals -2. So I'm going to connect these points to form the graph of my logarithmic function. Okay, that hooks up nicely. And then, let's see, I think I've pretty much got it. Now it's going to intersect that blue graph, but where it's going to intersect, I think is not really going to be anything special. I don't think there's anything important about where it intersects the blue graph. But this is the graph of g of x equals 2 log base 3 of x plus 4. And, well, what are the domain and range? Well, the domain, we can kind of look at the picture and see that the domain consists of, what is that? It seems to go out towards -4, but never actually has a function value at -4. So I think the input can be anything greater than -4. And then the range is still all of the real numbers. It's still all the real numbers because we took this graph here, which spans all of the real numbers vertically, if you're patient enough. And we're stretching it out vertically, so I think it still will do that. So the range should still be negative infinity to infinity. And as you see, there is a vertical asymptote at x equals -4. All right, so anyway, that was meant to be an example of how we can use inverse function thinking to get a graph of a basic logarithmic function. And then for a more advanced one here, we use transformations. So it may be helpful if you've not done graph transformations in a while to go back and review those.